Hey, everybody, welcome to Phase 6, the last chapter of the second trial. Ready? Are you kidding me? All right, let's check it out. What do we got? We are working with surface area and volume. This is a doozy. I actually made this as one note packet, but I'm going to split it into two separate videos because surface area, spoiler alert, sucks. Hooray! Let's do this. All right, so first learning about some three-dimensional shape stuff. So polyhedrons are the first type of 3D shapes, and the one that we're primarily going to, well, it's about half and half, going to work with. Polyhedrons where each face is a polygon. We worked with those last chapter. Polygons have to have all straight sides, at least three closed straight sides. So you can look at some examples down here and see that that does hold up. Prisms are made up of a polygon face and then rectangular sides that kind of extend back from it. So this is called a triangular prism. This would be a rectangular. This would be a pentagonal, and this would be a hexagonal, right? So you name it based off the non-rectangular sides, which we call bases. The bases are the non-rectangular sides, and then it's just extended back. They're all called faces. Every side of a 3D shape is a face. But the bases are the ones that are non-rectangular. And on a rectangular prism, the bases are the one that there's only two of, I guess is the way I could say, because like the front, back, top, and bottom are all the same size. So then these sides would be the bases. Right? These would be the bases. These would be the bases, the front and back kind of thing. All right, so those are prisms. Cubes, obviously, right? They're all equal sides all the way around. And then pyramids start with a polygon at the bottom, and then they come to a point. So they have bases as well. Bases are that side. And then they go to what's called a vertex, which is the top point. So that's called a vertex right there. So they go to a singular point instead of going to a mirror image of that same base on both sides. So that's what creates a pyramid. And typically we'll either have rectangular pyramids or we'll have triangular pyramids. You can have more, like I could make any of these prisms go to a single point and that would form a new prism, a new pyramid, but we don't work with those very often. They just get really complicated to work with. So typically rectangular bases, sometimes triangular bases, but that'll be about it for pyramids. And then we have the non-polyhedrons, and that's where one side, or at least it involves, just keep it general, involves curved sides. Or involves curves. So like a cylinder, right? A circle that's kind of, I actually named this baby shapes because originally when I was going to talk about this, I wanted to talk about it as like these 3D shapes kind of are like the offspring of two-dimensional shapes. When a rectangle loves a circle and they decide, they make a cylinder, right? This is the combination of a circle with a rectangle. A cone is the combination of a circle with a triangle. A sphere is two circles getting together. A cube is two squares getting together. Two triangles make a pyramid. A square or a rectangle and a triangle make a rectangular pyramid. A triangle and a rectangle would make a triangular prism. So this is really 3D shapes that we're working with are kind of like a combination of two-dimensional shapes. And we can see that when we start talking about cross sections. Cross sections are if you imagine you take a knife and cut through the shape. So if you're cutting horizontally, that's what this plane shows right here. I'm going to chop this way. And what you get is that little shape right in the middle there. You would get a circle. If you chopped a cone horizontally. Whereas if you chop that same cone vertically, so now if I'm chopping this way, I would actually get a triangle. And you can kind of see that right there. The part where the plane intersects the shape, that is the resulting shape. So a cone is the combination of a circle and a triangle. coming together in perfect union. If you'd like to pause and try to identify what shapes you'd get here, you're going to have a assignment that goes over that, so it might be good practice. If you don't feel like pausing yet, I'll just keep right on chugging. So here, if you cut a pyramid horizontally, well, it's going to be the same as its base down here. So if this is, it's kind of hard to see, but I meant for this to be a rectangular prism, or a rectangular pyramid, you would get a rectangular shape that comes out. Rectangle. Whereas if you cut it vertically, you're going to get a triangle out of it. So if we look back up to that one up there, if I cut vertically, I would get a triangle, but if I cut horizontally, you'd get the same shape as the base, just smaller because it's kind of pyramided in. So you would get the rectangular piece. If you cut one of these, you'd get a triangle in both directions. If you slice through right here, you're going to get a circle horizontally. And right here would give you a rectangle. So that's the idea of cross sections, cutting through either vertically or horizontally. You could cut it a diagonal, but then again, it gets kind of weird. You'll actually look at that a little bit in pre-calculus probably, where you have diagonal cross sections and you start getting ellipses. So instead of a circle, if you cut it a diagonal, you would actually get an oval, which can be called an ellipsis. So next thing, Platonic solids. So Platonic solids are made up of all the same sides and all the same angles all the way through in every single direction. This is what they make dice out of. If you've ever played Dungeons and Dragons, you've probably seen some of these other shaped dice, that it's not just all cubes. The most common, obviously, shaped dice is a cube, but these are the shapes that are considered balanced so that one side's not more likely to come up than any other side. And these are actually the only 5 that you can possibly make. So we looked at all those regular polygons in the last chapter. Well, out of all the regular polygons, these are the only 5 that can be formed into basically regular 3-dimensional polyhedrons. So that every single side and every single angle is the same. And again, those are called Platonic solids. And what I wanted to do for a second is show you how to make nets. You might have seen this in middle school. It's basically where you cut down all of the seams and unfold the shape. So if I did that with this tetrahedron, the first shape right there, well, we have an isosceles triangle. And then if I cut all those seams vertically, I could fold all the sides down to look like this. So that is what's called a net, where you unfold a 3D shape and put it back into 2 dimensions. And that makes it really easy to find surface area because you can physically see all the sides that you need to add up to find the surface area. A cube looks similar, but it has an extra appendage. Try. Pretend those are squares. So if I just unfolded a cube, again, if those were all squares, that would be the idea. Not even close though, right? That would be the bottom, front, back, left and right. But we're missing the top. So that's what I said, the extra appendage. Let's tack it on over here. You've got that one extra bit so that you could fold that over on the top. And tetrahedron actually is getting really, so we're not going to draw these other ones because they get really complicated, but I actually cut out an octahedron for you. This is what an octahedron would look like if you laid out its net. And you can see if I can try to fold it back right. It makes that shape that has the same side on every side. It kind of comes together to look like that. It's hard to hold, but you get the idea. And again, it gets, like I said, more and more complicated the more sides you have. They don't all make these clean little shapes like this. But that's the idea of nets, is that you can cut 3D shapes apart and lay them flat in order to be able to measure the surface area, how much space it would take to like cover this up. So let's actually talk about that. What the types of terms that you're going to see. So total surface area is like what we were looking at there. It's what the area of all sides added together. So if you include top, bottom, left, right, front, back, all the sides, like wrapping a Christmas present, without the bow wouldn't be included, and without any overlapping, you used exactly the right amount of paper to cover every square inch. That would be the idea of surface area. Now, lateral surface area doesn't include the top and bottom, so it is just all sides, not including top and bottom. Not including, I should call it, the bases. Using terminology we saw before. So like back up on a cylinder, just like before, those would be the bases. The two matching congruent shapes, the two congruent sides, just like what we had up here, bases. So all sides are the total surface area. That's what we primarily work with, but lateral surface area does come into play sometimes when you're only worried about the sides, not the top and bottom. Volume is the space inside. And it is also measured in 3 dimensions because you have a length, width, and height. So length, width, and height. It goes front, back, across, and up. So we're measuring volume in 3 dimensions. How much water fills up a swimming pool or a glass or something like that would be the idea of volume. And then this one copied kind of dark, so it might be hard to see. But I wanted to address at least the idea of slant height. So when we talk about cones and pyramids, we have kind of 2 different ways of talking about height, and we need different terms for each. So the one that goes straight from the center of the bottom, the center of the base up to the vertex, is called the altitude. And then the diagonal side down the outside is called the slant height. And while we're here, I might as well also address the fact that this right there, from that where the vertex comes straight down to meet the base, that would form a radius if this is a circle. So from the inside of the dead center of that cone out to the outer edge would make a radius. So some terms that are going to come up as we start doing the heavy lifting on the backside. All right, here we go. Brace yourself. So we're going to tackle volume first because volume's actually easier than surface area. Now, the formulas, I tried to kind of spell out here on the volume what the different pieces mean and like how the formulas are constructed. Except for this one, I can kind of just verbally describe that. So the idea of a rectangular prism is length times width times height. Now, if you have non-rectangular prisms, you're going to have to just find the area of a base and then you multiply it by the height. And that changes depending on what the shape of the prism is. So we looked at back over here, there's all kinds of different prisms you can have. And depending on what kind of base you have, that'll change the way that you find the area. But no matter what that shape is, once you know the area of a base, you're just going to multiply it by the height, right? Because you can think about it like a lot of those shapes stacked on top of each other is how you fill this thing up. I can cut out a bunch of pieces of paper that are all that same shape and stack them to fill this space, right? That's the idea that we're multiplying it by the height. So you need to find the base area and then multiply it by the height. How far from the bottom to the top? That is the height. And I included a couple formulas in there that you might have forgotten since middle school. The area of a triangle is half your base times the height of the triangle. So on a triangle, you've got base and height. And you're always taking half that because it's in shorthand, it's half a rectangle. So a rectangle would be like length times width, base times height, same thing. And in a triangle, exactly half of that rectangle is inside. Right? Half here, half there. So it's half of base times height. And on a trapezoid, you actually have to add these 2 areas, these 2 side lengths together. Call that A and B, the top and bottom here. Add them together and divide by 2. So again, that's that idea, that mid section. You're taking half of those 2 line segments, and then you're multiplying it again by the height. So this part tells you, I'm sorry, not the height there, the height here. So you average those 2 lengths, multiply by how tall the trapezoid is, and then once you know the area, that'll tell you the area of a trapezoid, then you multiply by the area, the height of the shape to get the full volume. So it's kind of double use of height, talking about 2 different things. The height of the trapezoid and the height of the trapezoidal prism. We'll see. You actually don't run into that one very often, but we'll see these in practice here later on if that's kind of confusing. Circumference and area of a circle. You're going to need to find the area of this circle and then multiply it by the height of the circle again. So the idea of height comes into play every single time, because if you make it taller, it's going to hold more stuff, right? So when you look at how much stuff fits inside, we always need to consider how tall the object is. We find the area of a base and then multiply it by its height. Now, once we start getting things that aren't straight as they go up, like cones pyramid in, or they kind of, they funnel in, I guess would be a way, it's going to involve fractions in here, because if we just did the base times the altitude, which is like the height, we looked at it on the front, from the middle up is the altitude. If we just multiplied the base times the altitude, that would give us a cube that's that shape. Right? It would have all this space in out here. If I filled in that space, I would get a cube from this shape. I don't want that. I want all this part missing. And it actually turns out that you could fit exactly 2 more pyramids around the outside in order to make the cube. So that's where it is 1/3, because it's 1 out of 1 and then 2 more would be 3. 1/3 of that base area times your altitude. Same idea here, 1/3. If we took a cone and kind of made 2 more and put them upside down here, we would get a cylinder. So instead of just the base times the altitude, which was like base the base area times the height here, we have 1/3 of that. And then on a sphere, it's 4/3 pi r cubed. Cubed, it's in 3 dimensions with the radius. 4/3 again, because it's not filling in all the way around. It gets a little complicated to talk about that one. So, and it's a pretty clean formula, because all you need is the radius. If you know the radius, you plug it in, you get your answer. It's pretty straightforward. So there's not a lot of interpretation or thinking on spheres. You just need a radius and a formula. All right, so I'm actually going to ask you to pause now and try to use those formulas down below. Let's specifically just say, try the first one, and then I'll go over the first one, and then we'll pause again and try the others. So go ahead and pause now and see if you can use this formula right here. You're going to find the base area of this cylinder and then multiply it by the height to find the volume. Pause now and try that. All right, so first job is to find the base area, find the area of this circle right here. So to find the area of a circle, we're going to use pi r squared. So all I need is the radius at this point. Pi times the radius, 15 squared. I just typed this straight into a calculator, and it gave me about 706.86. I just rounded off to the nearest hundredth. It's probably a good idea to round to hundredths so that we don't get too far off rounding, because we're going to use that rounded number again. And the more times you use a number that's been rounded, the further you get from the actual answer. So it's not a bad idea to use at least 2 decimal points here. So I take that, then I just have to do the base area times the height. So base area times height of 10 gives me 7,068.6 millimeters cubed. And that cubed, again, doesn't mean I'm taking this number to the 3rd power. It just means I'm measuring something in 3 dimensions. All right, we've got this way, that way, and the vertical. So we've got length, width, and height kind of on the cylinder. So we always include the exponent that shows how many dimensions we're measuring in. That's millimeters cubed, or cubic millimeters would be the better way to say it. 7,068.6 cubic millimeters is how much stuff fits inside that cylinder. All right, so see if you can do numbers 2 through 6. Keep in mind, they're going to get more difficult as you go. Try them. I promise it's more beneficial if you try and then look at answers rather than just waiting for me to tell you what to do. And watch out for when I start giving you diameters instead of radiuses. You got to cut that in half to use the radius. And on the last one, you're going to want to split this into 2 pieces. You're going to want to do half of a sphere and a cylinder separately. That's a tricky one, but try it. See what happens. There's no stakes here. You're just doing this on your own. Give it a shot. See how it goes, then we can go over them together. A lot of work. All right. Base area first. We always want to find the base area of each of these things so that we can then multiply it with our altitude, or in other words, the height of each thing. Unless we're working with a sphere, then it's just the radius is all we need. So here, my base is a triangle. It's the same at the top and bottom. So I actually use this base right here. and did area of a triangle is half the base side times the height of the triangle. Base times height of a triangle. So 1/2 times 1 times 2 is just 1. So I have a base area. This is 1 square inch right there. Well, then I use that base area times the height of the prism. 1 times 6 is just simply 6 cubic inches. On the next one, I need to find the base of the pyramid. So this area down here. Well, it's rectangular. So length times width. 6 times 6 gives me 36. And then I use that base, rectangular pyramid, 1/3 of the base area times the altitude. So 1/3 of 36 times 4 is going to give you 48. Again, just calculator work, right? You're just typing it in. So much of this is just knowing which formula to use and where to plug numbers into. All right, this one might have thrown some people off for 2 different reasons. One, the base is actually one of what you would think of as the sides, right? The base, you have to remember, are the 2 sides that are congruent with each other. The other 3 sides here are the actual sides. It's the 2 that match each other, where you only have 2 of them. Those are the bases whenever we're working, right? That's what we consider bases. The other ones are the sides, or the height for our measurements. So I found the base of that triangle. Now, it had a base of 8 and an altitude, or a height, of 7. So 1/2 8 times 7 gives me 28. So the area of this triangle is 28 square centimeters, or centimeters squared. And if that's the area, then I just have to multiply it by the height of this shape, or how far it is in this direction. Once I know this area, well, how far back does it go is the question. So I take that times 13, and that gives me 364 cubic centimeters. Similarly here, like I pointed out before, you have to make sure to take the radius whenever you're working with the area of circles. You want the radius, not the diameter. So I cut that 8 in half, and I'm using a radius of 4. The radius squared times pi is how I get the area of this circle down here. And then I use that number with 1/3 of that number times its altitude, which is 9. If I multiply that together, I get about 150.81. Finally, the volume of this bullet-looking feller. Well, we need to split it into 2 parts, like I mentioned. We're going to do a half a sphere, which is called a hemisphere. Have you ever heard of like the northern hemisphere of Earth? That's the top half, everything above the equator. We are in the northern hemisphere. Africa is in the southern hemisphere. Australia is in the southern hemisphere. So a hemisphere is half of a sphere. So I'm going to basically take the volume of a sphere and cut it in half, because I only want half of that space. So I took this volume of the sphere using 6 for my radius. Again, 12 would be the diameter. 6 is the radius. And I did half of that, and it gave me about 452.39. Okay, so I know how much stuff fits inside of this top bit. So now I need to know how much fits inside of this part down here. Well, to find the volume of a cylinder, I need to know the area of its base. So radius squared times pi will give me the area. Pi r squared is the radius of this base right here. And then I multiply it by the height to find out how much stuff fits inside there. And I got about 1,470.27. So if I want to know the total space that fits inside this shape, I just add those 2 together. The space here plus the space there gives me about 1,922.66 cubic inches. Oh, you can't see that. There it is. So you add the 2 pieces together. So again, like we looked at back with polygons, you can break the shapes apart into simpler shapes that you know how to work with. All right. A lot of arithmetic, a lot of calculator work. Make sure you are setting things up in this formulator, in the formula as well, and correctly, and taking your time to check your work as you go. If you have questions, as always, let me know.